Mm, Today I'm presenting this new paper, Emote. It's the same work as I present, not how to say, like it's the same line of work with the other presentation of mine, like I did in last month. But basically, we are the model they built is to generate the talking head videos from the audio and the one reference picture. And this is state of the art compared to the all last year's methods. Uh, okay, yeah, the idea is you have an input audio, the talking, singing, speaking, any kind of input audio, and the one single image of the portrait, and the model gives us the video. Uh, so they enhance the realism and expressions compared to the older methods, and to do that, they used end-to-end audio to video synthesis approach compared to the other methods that they used intermediate, some kind of 3D models or facial landmarks. Mm, Talking head video generation is challenging because of the rich facial expressions in the human face, and it combined with the audio, it's not one-to-one. It's also one of the biggest challenges. One audio can be mapped to many kind of videos, so that's another challenge. And the third challenge is the fluid motion, like the how to make the video like smooth enough, like the frames don't differ much from each other in terms of the head pose. So this work used, as I said, uh, directly audio to video synthesis without using any intermediate 3D models or facial landmarks. And they used face locator and how to say weak supervision, small weak supervision models to make the transition between frames smooth and maintaining fluid motion. And they have also added a small network to preserve the identity over overall the video. So it's basically the whole model based on Stable Diffusion 1.5, and they kind of changed some parts of the Stable Diffusion. If you don't know, Stable Diffusion is actually proposed to generate images, to generate high quality images. It's been like some time since Stable Diffusion, and Stable Diffusion is also like evolved. Now currently the GPT, DALI, and what was another one? Yeah, this generation models are based on diffusion somehow, denoising diffusion, and Stable Diffusion is kind of the first ones of them. And if you can generate image with Stable Diffusion, you can also generate video frame by frame, but it's going to be like very expensive. Stable Diffusion is all of the expensive, so. And the contributions of this paper is ReferenceNet for identity preservation, some audio layers to incorporate the audio input to the output, and temporal modules to make the motion smooth. Okay, the bad side is that they don't give much information about architecture. The paper is very short, and and they also don't provide the code. I don't know, maybe it's like too good, or maybe it's from Alibaba Group, so maybe it is commercialized, so they didn't provide code. And yeah, basically this part is the diffusion process, a little bit harder to process because the diffusion process goes step by step. Like we feed the answer of the first step into the second step, so this is kind of loop. Where we start, we have audio, we have just noise to starting noise, and we have what we have reference image. In the beginning, these motion frames will be noise, all like very similar to noise. After the many steps, like one step, we will produce, and this is UNet, in this UNet, but the change, it's changed a little bit. Like we have UNet with first layer, we have self-attention, to add phase region locator with noisy latent frames. This phase region locator is used to as a weak supervision to make the head motion more realistic. They incorporated here reference attention, the second layer. In the original stable diffusion, stable diffusion also accepts text input, text condition, but here we don't have text prompt, so we change it to the reference attention, and reference attention data comes from reference net that is responsible for extracting features from the reference image and blending them to the motion frames. Then we have audio features. They use wave to wake. This is like famous audio to vector, yeah, by name, audio to vector encoder. And this is I think this is state of art. So they just used this model as a freezed with weights, with pretend weights. Yeah, you can see like snow here. And then we have speed encoder. Speed encoder is it predicts the speed of the head motion. It is also used as a weak supervision. We'll talk about a little bit later about this too. Okay. Yeah, in one step we have noise input, and we get some less noisy frames, and we feed them into reference net. But here, reference image is blended only in the beginning to make the process more efficient. And yeah, this just continues many steps, and yeah, I don't know, after some hundreds or thousands of steps, we get some good video. Okay, this is about like we control modules. These two modules, phase locator. As I said, phase locator is a very shallow convolution neural network to predict the phase bounding box, and it is used to kind of constrain the generation, so the phase appears at that place. And speed control is used to smooth the dynamics of the head. And yeah, it is it is it uses audio, yes, audio and the frames to predict some uh, predict the predict some buckets of the speed. It first like divides the video or the audio, like in this almost the same meaning, in a buckets, and sets speed value, head speed value to that buckets. So the stable diffusion model uses these speed values to constrain the head movement. And in training process consists of 3 stages. In the first stage, it is just pre-training with images. I think they didn't pre-train the stable diffusion, or they pre-trained the stable diffusion, but first they get the stable diffusion weights, pre-train stable diffusion weights, then they pre-train the changed. In a sense, they initialize the process with the original stable diffusion weights, then they just pre-trained with single frame, like making pre-training with single frame is like almost copying the reference image without even audio. It just works with one image. Then they added in the next stage, they add frames with temporal modules. This stage doesn't train the temporal module because we don't have temporal information. We have one image. Then we add temporal module. In this stage, we also integrate the audio cues or audio features. So the most part of the model will be trained. And in the last stage, the weak supervision models, speed layers, and face locator module is incorporated to refine the generation ability of the model. And for dataset, they collected their own 250 hours of talking head videos in the internet. Supplement to this HDTF and VFHQ. These are like mostly used datasets in this kind of research, and they used these datasets also for training, but kept the 10% of the HDTF to test, and they ensured no overlap between the subjects in the training and test set, so it doesn't so the model have never seen the subjects in the test set. And to compare to the other models, they use this metrics, FID, Flathead Inception Distance. It is used in generative images to measure the visual quality and diversity of generated frames. And this is I think we use some pre-trained visual image encoder. Like I think VGG or Inception, and we use the later feature map to compare with the reference image. And SyncNet is just another network to just evaluate the synchronization of just lip movement. And FSIM, facial similarity, to assess how well the model is preserving the identity across the whole video. And Frequent video distance, I think this is just generalization of Frequent inception distance. But I don't know how it works. And yeah, no, the FEFI, the expression Frequent should be expression Frequent inception distance evaluates the expressiveness of generated spatial expression. Yeah, as they compared, so SyncNet should be big. I mean, greater is better. This is just a neural network to build to compare the lip movement. So it is not kind of mathematical metric in terms of that. Yeah. So in terms of lip synchronization, wave to lip is better because wave to lip model just produces lip movement. It doesn't produce any face movement, so it is better because of that. In other metrics, in other metrics, it shows their method is better. But I don't think this metrics kind of captures the whole potential of the generative models. I think it's also like hot research area to assess how well the generative model is, and maybe we can we can see some results. Yeah, this is AI generated videos. I don't know, I showed the last time the videos, but the older works you can see, and we can feel like this is AI. Somehow you can like detect some facial artifacts, but now it looks like just human. And even this reference picture is generated by AI. It is Mona Lisa generated by, I think, DALL-E. Yeah. And speaking.
When I was a kid, I feel like you heard the term.
Yeah, this is so kind of motion is fluid.
Crying is the most beautiful thing you can do.
In terms of like facial expressions and even the eye blinking. Yeah, eye blinking was problem in last works as they control eye blinking by another control signal, but it wasn't good enough. And yeah, this has limitations. I think the biggest limitation is time consumption and just generally the resource consumption. They didn't write about anything about like how many GPUs they use or how many hours of training or how much time we need to inference. But I think it is very high, so they just didn't show it because the other models, the models based on GANs or based on the simple transformers, it was taking like 1 minute to generate 2-3 minute video, and I kind of expect this like takes half an hour to generate 10-minute, 5-10 minute video. And it also takes, I think, very much GPU because stable diffusion already takes like a lot of GPU to generate one image, but they are generating frames. So this model should be very expensive. And they also wrote that there is some artifacts in terms of generation. In generation, occasionally the hand comes into the scene, and they didn't show example, but they say that is one of the limitation, and it can be avoided with in the future work with the help of like some control signals to control the basically to control the the content, video content, like to control the head motion with like manual control signals. And yeah, that's it. Thank you.